So we already saw how to get our temperature data in from our 6 different temperature sensors here, and we pulled off the first one and plotted it against time. And we noticed that it had a lot of noise in it. So I can imagine that there's a fairly steady mean value in there, and if I could just smooth off that noise, I could get a better idea of what the mean value was that I'd get by averaging multiple samples. So let's go down here a little further and see what we can do with that. So I've got t and t0. I'm still going to have lowercase t for the time, but I'd like to smooth off t0. So let's make a copy of t0. So it's going to be exactly like t0, but let's call it t0s equal to a copy of t0. And that ran okay. And what does t0s look like? Yeah, it's a big long array of temperature numbers, so it's just what we thought it was. But let's try to smooth it off. So now I'm going to go and I'm going to say that in a region over that whole range of values, so what's the shape of t0s? How long is it? Well, we know from up here before that it went on for about 40,355. What is the length of t0s? Yeah, it's 40,354. The 55 was because we had the strings up on the top, the titles. So that's how long it is. So I could go and change the values on different parts in t0s by averaging over that space. So let's go for I in a range from 0 to the length of t0s, so all of them, and I've got to have a colon there to tell me I'm going to have an indent. Now I've got the indent. Let's make t0s I. So let's make the average value equal to the mean, the smoothed off value, the mean of, it needs to be an NP mean because we need that numpy function. And we're going to take a mean of the raw data, that's the t0 data, but we don't want the mean of the whole thing, we just want a mean of part of it that's close to the part that we're interested in. So let's go from, let's say I minus 2 to I plus 2. So that'll take 5 different points. It'll take I, 2 in the old time, 2 in the new time further ahead, and average them all together. And what do we get? We get a runtime warning. Mean of an empty slice, invalid value. I think we did something wrong here. And I think what's happening here is when I go from a range starting at 0, then I minus 2 is negative 2. That's outside the actual valid range of the temperatures. So we better go from, let's make n equal to 2, and we'll go from 0 plus n to the length minus n. So we'll only do it on some of the values in the middle. Let's see how that runs. That runs without causing us any trouble. That's good. And we can do a plot. Of t and t0. That's the plot we had before. And sure enough, it looks the same as it did before. But now we'll plot the smoothed version. Of t and t0s. So that's the smoothed version of the temperature data. Let's see what happens. It takes a while to calculate because there's quite a lot of data to manipulate there. Well, the orange stuff here, it's still noisy, but the noise is much smaller. So by averaging even over a few samples, we've managed to make that noise smaller. And let's make that n and n just so that it's n all the way through. And let's make n equal to 20 instead of 2. It's going to take even longer because it's using more points in each average. But it got smoother, closer and closer to the mean. Let's make it 200. So there's still some noise in here going on, but it's a lot smoother sample. We've got noise out here at the edges that's coming from the fact that we can't really work right out at the edges to do our averaging. So that's looking way better than this noisy stuff. So that's a moving average. We've created a moving average of our data, and we've gotten rid of a lot of the noise. Now that was really pretty easy in Python, but to do that we had to have the array, all of the data to work with. And in the Arduino, we're not going to have all of the data. There's just not enough memory to store it all. So we're going to have to explore some other ways. And another way that we can do this is exponential smoothing. And the idea with exponential smoothing is that we'll make an estimate, and then on our next sample we'll adjust that estimate, but only part way towards the new sample. So we're going to have a weighted average of the old value and the new value. Now in exponential smoothing we've got this idea of a time constant, and usually we call it tau. And it's some time value that we are going to think of as the averaging time. So if I make that 0.1, that's 1/10 of a second. So this is going to smooth things out so that we only see changes that are happening sort of at the speed of 1/10 of a second, not way faster than that. And I'm going to make another copy. I'm going to make T0 smoothed. I already called it T0S up there when I did the averaging. Let's call it T0E then for exponential smooth. And I'll make it a copy of the T0, just like I did before. And then I'm going to, I've made a copy of it. I'm going to have to go over all of the values and estimate what I've got. So I'm going to start for I in the range from 1 up to the length of T0E, whoops, capital T, 0E. So that's starting at the second value. We won't do the 0, 1, but we'll start at the second value and go all the way to the end. I need to know what the difference in time was between the two times. So I'll get difference in time equal to t at I minus t at I minus 1. So that's the time since the last sample. And then here's the tricky part. We need to use this weighting that's going to be equal to the difference in time divided by the time step, or sorry, the time constant. And that value there, that is, as long as the time step's really short, that's going to be really small. So this weight is only going to be a small fraction of 1. It's not going to be a large number. But just to make sure that things work out okay, let's make sure it never gets bigger than 1. So we'll use a minimum value that's either dt on tau or 1 for our weight. And then we can make an estimate of the smooth value, the exponentially smooth value, T0e at time I. So at this step, it'll be equal to whatever it was at the last step. So at I minus 1. And we'll have to multiply that by something to account for the fact that we're taking a little, mostly that, and a little bit of the next one. So I'll multiply that times 1 minus W, and then I'll add T0 at time I times W. So 1 minus W plus W is just 1, so we're doing a weighted average of these two, putting most of the weight on this one. And this was whatever we estimated the temperature was at the last time step. So we're only going to change it a little bit each time we go through, each time we go along. And when we do this on our Arduino, this is really easy because we only need to keep track of two values. What was it last time? What is it now? And we'll just keep updating those two values. So that makes life a lot easier. And that's all it's going to take, I think, to do that smoothing. And the smoothing ran. So let's plot, plot time and the smoothed values, so that's T0e, and see what that graph looks like. I don't know why that's taking so long. Oh, because I put the plot inside the for loop. That was dumb of me. I will need to go up here and stop the kernel. So I'm going to restart and clear output. So that should restart everything. I'll need to run all this stuff again, but it shouldn't take too long. So that makes sure that I've done all the calculations on the way there. Okay, so there's my averaged data, and there's my smooth data with a time constant of 0.1. That doesn't look as good as that averaged data. And let's just make them look alike. So I'll do a plot, first plot will be a plot of time and the original temperature values. And I'll run that. And when I'm not trying to plot it every single time, it really does come out a lot faster than this calculation. So what if I make the time constant larger? Let's average over a second sort of a time frame. And now I'm getting something that's looking a lot closer to that moving average. it's still got a few spiky glitches in there that I'm not sure where they're coming from. But if we make that 3, those glitches are pretty much gone. And those values are looking about the same. So we're getting the same kind of behavior. Except we see it takes a while for it to move from the original first estimate up to the eventual mean values. So smoothing, we've got this startup transient. Moving average, we have to have all of the data in advance, and we've still got this noisy portion out here at the edges that can be a little difficult to account for. So that'll let you do some smoothing and some averaging in assignment 2.